Welcome to Unit 9 of this course. In the last two units, we saw what is called linear temporal logic, LTL, and we also saw algorithms for model checking, LTL, on transition systems. In this unit, we would see a different logic called computation tree logic. The first task would be to look at a tree behavior of a transition system. This will be explained in this module. Consider this transition system. These are the states and these are the atomic propositions which are labeled in each state. We have so far been looking at paths in this transition system. For example, say this is S0, S1, S3, S3, S3 and so on. Then there is this path S0, S1, S2, S3, S2, S3, S2 and so on. So we have been looking at infinite paths. Once we have paths, we can look at traces by restricting to the atomic proposition labels in each state. So S0 is labeled by P1, S1 is labeled by P2, S3 by P1, P3 and so on. So each path gives rise to a trace. And this trace is an infinite word. So we have been looking at ways of expressing sets of infinite words. This is what we have seen so far. In this unit, we will view the transition system as a tree obtained by repeatedly unfolding the transition system. Let us see what we mean. This is the same transition system. Let us start from this initial state and try to unfold the transition system. So at S0, there is only one transition, which is S1. At S1, there are two transitions, S3 and S2. So you have these two transitions going to S3 and S2. Now at S3, there are again two transitions going back to S3 and to S2. So instead of giving this as a loop, we give it as a tree. So this is the S3 obtained after doing S0, S1, S3. This is the S3 obtained after doing just S0 and S1. So these two are differentiated. Similarly, at S2, there is only one transition going to S3 and so on. So this is giving us a tree. At any point, there is a node and then there are children corresponding to the edges in this transition system. This is an infinite tree. You can keep continuing. This path is S3, 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 S3 and so on. And then you have S2, S3, S3 and so on. So you know how this transition system unfolds. This tree is called the computation tree of the transition system. It is telling us the process of execution of this transition system. We know that LTL talks about properties of paths. We will now talk about properties of trees. Suppose you have a tree like this. We want to ask whether the tree satisfies certain properties, not just paths. We want to talk about this entire tree. Does it satisfy a property or not? We will start off with many examples. Look at this tree. For clarity, I have not given the names of the states. Also, I have not given the labeling of atomic propositions on each state. Assume that there is an atomic proposition called red. So these states have been marked red. This tree satisfies the property that there exists a path which satisfies f of red. So look at this path. If you look at this path, at some point of time, red is true. So this LTL formula f red says that at some point of time, red is true. And in this tree, there exists a path. There are many paths where red is true, but as long as there is one path where f red is true, this tree satisfies exists a path f red. Okay, I will give these properties in English. Later on, we will see notations for these properties. Look at this tree. Look at this path. Assume that this path can be extended to a path where every node is colored red. That means every node, every state in this path satisfies the atomic proposition red. So there exists a path which satisfies G red. Correct? G of red is true on a path if every node in that path satisfies red. So here there exists a path which satisfies G red. Look at this. This tree satisfies this property. There exists a path satisfying X red. Look at this path. So some continuation of this path. If you look at that path, it satisfies X red. This is the initial state of the path, and then the next state satisfies red. So X red is true on this path, and in this tree there exists a path which satisfies X red. Let us look at this tree. Here there exists a path satisfying blue until red. Correct? This is the path, some continuation of this path, and in this path blue is true till the point where red becomes true. So, and this can be expressed using blue until red, and the fact that there exists a path satisfying blue until red is expressed here. And there exists a path which satisfies blue until red. If you had noticed, in the last 4 examples, we were saying that there exists a path satisfying some LTL formula phi. An LTL formula gives you a property over paths. And for trees, the first type of property that we want to talk about is there exists a path satisfying an LTL formula phi. And the notation for this is E. E stands for exists a path. And then you can follow it up by saying, by using an LTL formula. E phi tells that there exists a path which satisfies the LTL formula phi. There could be some trees which satisfy this and some trees which do not satisfy it. So in this notation, exists a path satisfying f red will be written as E f red. You know what f red is, and E is the new operator that we have defined in this module. E f red is true in this tree because there exists a path satisfying f red. Similarly, in this tree, E G red is true. You know what is G red, and now E stands for exists a path satisfying G red. Similarly, this becomes EX red because there exists a path satisfying X red. And finally, this tree satisfies E of blue until red. So exists a path satisfying blue until red. This blue until red is a property of a path, and this E operator will say that there exists a path which satisfies this property. Now, we have seen the E operator. Let us see one more type of property on trees. Look at this tree. This tree satisfies the property all paths satisfy F red. You look at all paths in this tree. For example, look at this path. Any continuation of a path in this subtree will satisfy F red. So there are many paths here. One that goes left, this one, or this one, the one that comes here, and so on. So any path obtained after this node will satisfy F red. Similarly, look at this path. Any path after this will satisfy F red. Similarly, any continuation after this will satisfy F red. Similarly, any path from this continuation satisfies F red. And since here there is already a red, any path obtained by continuing this will satisfy F red. So in particular, all paths in this tree will satisfy F red. So if you just look at some path in this tree and you write it down in a linear way, you will see that red will be true at some point. So all paths in this tree satisfy F red. Previously we were looking at exists a path satisfying F red. Now we say that all paths satisfy F red. Look at this tree. All paths satisfy G red. You look at any path and G red is true. That means red is true all along this infinite path. So this tree satisfies all paths G red. Okay, so this is a property. All paths satisfy G red. Look at this. All paths in this tree satisfy X red because the children at the first level satisfy red. So you look at any path, X red will be true in that path. So you take a path and write it in a linear way, X of red will be true. What about this? All paths satisfy blue until red. Because you look at any path, till red is true, blue is true. So here all paths that are continued after this state will satisfy blue until red. Similarly, all paths after this continuation, after this continuation, after this continuation, and so on. So all paths in this tree, you try to find some path in this tree, and every path in this tree will satisfy blue until red. So this is the second type of property over trees. All paths satisfy LTL formula. So an LTL formula is a property over a path, and over a tree we have this additional thing which says that every path satisfies this LTL formula. And for this we have the A operator. When you say A phi, it means that all paths in this tree satisfy the LTL formula phi. So this translates to AF red. This tree satisfies AF red. This tree satisfies AG red. All paths satisfy G red can be written as AG red. This is the notation. Similarly, this will become A of X red. And this becomes A of blue until red. So all paths satisfy blue until red. So we have seen two types of properties over trees. There are two operators A and E. When you say A of an LTL formula, note that an LTL formula is a path property. Okay, that's why I have emphasized this. When you say A of some path property, it means that all paths in this tree satisfy this path property. When you say E phi, it means that there exists a path satisfying the path property. These are the two operators and they are very simple. What we will now do is we will try to do a mixing of A and E. Let us see what we mean. So recall, EF red is there exists a path where F red is true, and AG red is all paths satisfy G red. Now look at this tree. This subtree satisfies G red, and there exists a path to the root of this subtree. This looks like a mix of E and A. Indeed so, there exists a path such that FAG is true. There exists a path where at some point of time AG red becomes true. So you look at this path, at some point of time you reach a state that satisfies AG red. Look at this state. All paths starting from this state satisfy G red. So we say that this state satisfies AG red. So that is this part of the formula. And then this state is reachable via a path from the initial state. So there exists a path which reaches a state where AG of red is true. So this is the first example where we have mixed A and E and we are getting something interesting. So you reach a state such that the subtree below it satisfies AG red. Here, look at all the paths. At some point of time, you reach a state where AG red is true. From this state, AG red is true. From this state, AG red is true. From this state, AG red is true because all paths out of this state satisfy G red. Similarly, all paths out of this state satisfy G red. So AG red is true here, AG red is true here. Similarly, AG red is true in this state. And hence, you have this AFAG red. This was EFAG red. This is A. From all paths, you reach a state that is given by AF such that AG red is true. This is simple. From all paths, you reach a state from which AG red is true. Let us now look at another example, but before that, recall EG red is there exists a path where G of red is true, and EX red is there exists a path where X red is true. Now, EGEX, look at this path. In this state, EX red is true because there exists a path out of this state, which is this one, that satisfies X red, right? From this state, EX red is true. Look at this state. From this state, there exists a path where X red is true. So this state satisfies EX red. Look at this state. There exists a path satisfying X red. So starting from this state, look at this path. If you look at this path, next of red is true. Similarly, start from this state, look at this path. Or rather, start from this state. In this state, EX red is true because there exists a path out of this state satisfying next of red. Similarly, you can assume that from this state there exists a path satisfying X red. So if you look at this path, every state in this path satisfies EX red. So this path satisfies G of EX red, and since this is a path in the tree, we write exists GEX red. This is a slightly complicated example. Please try to understand it step by step. This is another tree which satisfies the same property, EGEX red. Look at this path, the leftmost path. Every state satisfies EX red. Okay. Note that in this, it doesn't mean that the path that we choose needs to be this one. For example, in this state, EX red is true because of this path. Similarly, EX red is true in this state because of this path, and so on. So every state along this path satisfies the fact that EX red. This is a fairly complicated formula. This says that there exists a path where something until something is true. You know what is EX blue? Look at this state. Forget about everything, just look at EX blue. This state satisfies EX blue because there exists a path satisfying X blue. Similarly, this state satisfies EX blue because there exists a path satisfying X blue. Now look at AG red. Forget everything and look at AG red. You know that this state satisfies AG red because all paths starting from this state satisfy G red. So this state is said to satisfy AG red. Now we said this satisfies EX blue, this satisfies EX blue, and this satisfies AG red. So there exists a path that satisfies EX blue until AG red. Okay. So this AG red is true in this state. EX blue is true in these two states. So we can write this formula which says that EX blue until AG red is true on this path. So E of EX blue until AG red. So we have introduced a tree view of the transition system. What is our goal? We want to talk about properties of these computation trees. The computation tree of a transition system is obtained by repeatedly unfolding the transitions. And to talk about properties on trees, we need some notation. We know about properties over paths, so that has been extended to trees by using the E and A operators. E says that there exists a path that satisfies a certain property. A says that every path in this tree satisfies the path property. And the last 3 or 4 examples that we saw had a mix of E and A, and this could give certain complicated properties over trees, saying that there exists a path which reaches a point from where the entire subtree satisfies certain properties. That is an important thing which could be useful in practice. And we also saw some other property saying that there exists a path where something is true until something else is true. And each of these somethings were had nested E and A. This was the EX blue until AG red. So E of EX blue until AG red. So we have given you an idea of E and A and how to mix E and A to get complicated properties. In the next module, we will give the formal syntax and semantics of a logic over these computation trees.